Thank you very much. It really is an honor to be selected as a keynote lecturer for this very important, prestigious conference. And so thank you, the organizers, Layman Wang, and the others for inviting me. And I will talk about performance-based seismic assessment of slope systems. And this work was conducted with Jorge Macedo, who's a professor at Georgia Tech. Seismic slope stability is a pressing problem in geotechnical earthquake engineering. We know that from past events such as the Alaskan earthquake and the Taiwan earthquake in Christchurch, but also when we anticipate a seismic event and we have to put in a mitigation system, we have to have a good sound basis in which to evaluate the design of that system and the performance of that system. We must remember, however, as we talk about seismic slope displacement, that the Las Palmas gold mine tailings dam failure is a too frequent example of cases where there's a significant loss of strength, in this case, soil liquefaction, that leads to a flow slide, which leads to large deformations that are not controlled. And unfortunately, the slide killed 4 people. And so it's mindful as you talk about seismic slope displacements to remember the most critical issue is number one, are there materials within the foundation, within the system that might lose significant shear strength as a result of cyclic loading? And obviously, if you've put in your post-liquefaction strengths and you have a post-cyclic static factor of safety less than 1, this flow slide is possible and you need to direct your attention to that. If not, there's still the question of will the system undergo significant deformations that may jeopardize system performance. And that's where it's useful to have a tool that estimates seismic slope displacement as an index or a way to judge that performance. Now, when we look at seismic slope displacement, we're looking at shear-based mechanisms. The Newmark sliding block analogy is a shear-based mechanism. It's slip along a distinct failure surface, but we also, because we don't have a rigid block, and this is a clay slope shown here in a model study where we actually did have a failure zone, a failure surface develop, and so there actually is slip along a defined surface. But because the system that's responding is not rigid, there is distributed shear, and so the overall movement is the combination of those two things. Now, very importantly, a shear-based mechanism should not include volumetrically induced deformation, and in this case, it's nil, but in other cases, it can be the dominant source of deformation. So it's important that you include the volumetrically induced deformation and add that to what you calculate with the shear-based mechanisms to be able to estimate the total displacement. I'm focusing on shear-based displacements with the seismic slope displacement today. When you look at the key components of seismic slope displacement analysis, it's always useful to evaluate them in terms of how do they handle dynamic resistance? How do they handle the earthquake ground motion? Do they capture the dynamic response of the system that may move, or do they assume it's rigid? And how do they perform the seismic displacement calculation? Nearly everyone uses the yield coefficient to represent the dynamic resistance. This is the seismic coefficient that results in a factor of safety of 1.0 in a pseudostatic slope stability analysis. So you start off your dynamic analysis, your dynamic assessment, doing a static analysis. And so you need to be mindful of that when you choose your sections, and choose more than just the section that gives you the lowest static factor of safety. Look at the one that gives you the lowest KY. Really look at the ratio of KY to K max, which we'll talk about. There are a number of things that are important to doing this, but in a clayey slope, such as this dam case that I'm showing here, it's soil strength that's really pressing. And so an issue comes up is estimating the peak dynamic strength of the clay materials. What we normally do is focus most of our attention, deservedly so, on the peak static strength. There are a number of complications in terms of how variable it is laterally and vertically, over consolidation ratio, anisotropic responses, stress path. All those things are critical to come up with the best estimate of the static peak strength. And then we typically modify it based on rate effects and cyclic degradation. And I'm focusing on those two because those are the most pressing in most of the time. Rate effects, as we know, when you load a soil at a much higher rate of loading, the resistance increases, and that can be a factor from 1.4 to 1.6, or it depends on the clay and the change in strain rates. Cyclic degradation, as you develop cycles of loading, you do soften the soil, you build up some excess water pressure, some softening, and after shaking, you can get a post-cyclic strength that's less than what it was before that. And so when we look at adjusting our static peak strength, it's important to remember rate of loading effects, cyclic degradation, which I discussed briefly, and I think you're familiar with those. But also remember this progressive failure. You're not likely to get to the peak strength in a strain softening material at the same time along the entire failure plane at exactly the same time. And so that will be a value less than 1. And then remember the distributed shear deformation. You can have cycles of loading that don't quite reach peak strength, but still include some deformation. Now, when we do these adjustments, we often end up with a static strength that's multiplied for rate effects, increased, reduced for cyclic degradation, reduced slightly for the other effects, and we often end up with a value that's very close to what we had statically. However, that shouldn't always be the case. The peak dynamic shear strength varies with the loading. It varies with the earthquake motion. So if we have a slope stability problem and the clay's the same, the slope's the same, and it's hit by a near fault forward directivity ground motion with one big pulse, you will have the rate effect, but you will not have the cyclic degradation effect. And so it's appropriate to use a peak dynamic strength that's 20% higher than the static peak strength. For that same clay, for a different loading, a long duration backwards directivity motion or a large magnitude event, we have the competition between rate effects and cyclic degradation. However, because there's so many cycles of loading, the degradation factor for this case is lower, and it's entirely appropriate to use a peak dynamic strength that's 20% less than the static peak strength. And so it is important to realize that once you've picked a peak static strength, it should vary depending on the ground motion that you're running through the analysis. Now that's the peak dynamic strength, and that would be appropriate if we have a strain hardening material or we had calculated limited displacement. But if we have a strain softening material, which are the more troublesome materials, as the earthquake induces a strain greater than the failure strain, then we're going to need to rely on something like the vane shear test that shows that the peak is not maintained, but we move down toward a residual and then eventually with full remolded shear strength. And so the dynamic strength that's appropriate for limited deformations is not appropriate as we calculate larger amounts of displacements. And therefore the KY, the yield coefficient, which is a function of the strength, has to vary with displacement and be compatible with the level of displacement. In terms of the earthquake ground motion, many methods focus on the peak ground acceleration. That's only appropriate if the system that is sliding is rigid and has a fundamental period of 0. But we often have systems that have some flexibility, and just like we do in structural earthquake engineering and we do in other problems in geotechnical engineering, we should recognize that a better indicator of the seismic demand on this system, if it has a period, for example, of 1 second, is the spectral acceleration at 1 second. You could have ground motions with exactly the same PGA that are very different in terms of how they load a 1 second system. And so we should appreciate that. And the third thing to recognize is that the system that's moving is not rigid. And the other important thing is you have incoherent ground motion. Part of it's accelerating to the left, while part of it's accelerating to the right. This is the concept that actually Professor Chopra developed initially for dams, and it was brought over by C.D. Martin to earth dams in 1966, and it's a part of many of the methods. It's this idea of this equivalent acceleration. For a 1D case, it's the shear stress time history calculated on a horizontal plane, divided by the total vertical stress, because that represents the mass. So we're not using effective stress here. This represents the mass. And then the maximum value of that divided by G, because acceleration is in G, gives us this dimensionless seismic coefficient, the maximum, Kmax. Kmax depends on the ground motion. There's a nonlinear factor we need to think about, so it's not just directly proportional to it. But what I want to emphasize with this slide is the sliding mass period matters much in terms of how it relates to the mean period of the ground motion. And as we move to longer systems with higher fundamental periods, we get a lower seismic loading, a lower Kmax value. And so we need to have an approximate number. We don't need to be precise here in most cases, but we have to estimate the fundamental period of the sliding mass because it matters. And for level ground, we have the familiar equation, 4H over VS. For non-level ground, 2D effects, we can use an equivalent or effective height. So we should use an average shear wave velocity where we weight the shear wave velocity by the mass by each shear wave velocity that represents it and come up with a mass-weighted average shear wave velocity. We should do the same for the height. So we end up with an effective height. And so, for example, in this case, where it is largely 1D, and you say, I'll break it into 10 slices for an approximate estimate of what the natural period will be. I take each of these up and go through these calculations. I come up with 4H over VS because H is essentially the effective height. In the 2D case, if you go through and add these things up, you'll end up with an effective height of 0.65H. If you put that in there, you'll end up with the very familiar Embraces and Sarma 67 2.6H over VS for the 2D section. All other sections for at least 2D analysis and 1D analysis fall between those. And so we looked at a range of different ones and calculated them with this approximate method as well as more precisely. And you end up with an effective height of 0.65H to 1H. And if you think that this mass is contributing to this dynamic response, you can do the calculation for just the sliding mass. You can also include the mass to the left and look and see if that matters. Now that's for base sliding. If you're looking at movement near the crest and it's shallow sliding, then the system itself is nearly rigid. And so we use the spectral acceleration at 0 period, or the peak ground acceleration. And it's important to include the 1D side effects because the rock motion will be amplified or de-amplified depending on the soil and the intensity of the motion for 1D side effects. But then it's important to bring in the important effect of topographic amplification. And that's a 1.5 factor based on the work of Ashford and Sitar for steep slopes. In an independent study that just happened to be about the same time, we do talk every once in a while. We found out after we did our study that for moderate slopes, we had 1.3. Obviously, it'd be 1 for level ground. And then for the special case of a dam crest, the work by Park and Casita, where they did a number of analysis and checked things, have a relationship for estimating that. The other thing is the seismic displacement calculation. We typically have done what is the decoupled approximation, where we estimate the dynamic response with a program like Plaxis or Quad 4M or FLAC that says there is no sliding on the slide plane. And then with that equivalent acceleration time history, we double integrate it with the Newmark analysis and calculate how much sliding there is along that interface. So it's clearly theoretically an approximation. We have continuity of displacements here. We have no displacement here. We have displacement being calculated here. Chopra actually, for concrete dams, developed a method to do a coupled sliding. We built on that, and this is the work that Ellen Rathje and I did about 20 years ago. George Gazaitis and others have done a significant amount of work in this area. But with today's tools, we can actually limit the maximum force for base sliding to be limited by the KY over the weight and allow the system to slide when it wants to slide, get stuck when it comes to rest, and actually do a fully coupled analysis. For many cases, it doesn't matter because small displacements with the decoupled analysis is relatively small with the coupled analysis. When you calculate large displacement, we typically are being conservative when we use this decoupled approximation. When we're in the range of 10 to 100 centimeters, which for some systems is an important range, we can be unconservative with the decoupled approximation. Most people think that it's always conservative. It's not true. And the motions that tend to make us unconservative with the coupled analysis is larger are pulse motions in the near forward directivity. In the end, we're calculating a seismic slope displacement versus a yield coefficient. We don't want to just calculate it at one value, but we want to understand how close we are to the cliff. So we'll do a sensitivity analysis and look at the range of KYs. We'll look at different velocity profiles. But I'm emphasizing how important the ground motion is. Just 5 ground motions here that are all fitted to a response spectrum, very different calculated responses. And so there's nothing more important than the input ground motion. And then also to remember that D that you calculate, it's just an index of seismic performance. Well, if it's an index of the seismic performance, we can use a simplified method to get a sense of what the answer is. It can be used as a screen analysis to tell us when we don't have an issue or when that issue is in the range where we should do more advanced analysis to gain insight. The work that I recently completed with Jorge Macedo is an extension or builds on the work that I originally had performed with Value Travis Zero. At that time, we only had the NGA West ground motion database, which had about 700 ground motions. Now we have NGA West 2 from the Pacific Earthquake Engineering Research Center. So we had nearly 7,000 two-component motions. We don't use each individual component as one motion because they're correlated. We use them together. And so we get one displacement for each two-component of horizontal shaking for this 1D, this movement in one direction. Looked at a updated slope model, nonlinear, fully coupled, deformable sliding block, ranges of TSs and KYs. He performed nearly 3 million analyses to really understand how things vary as a function of the ground motion. And the most efficient and sufficient ground motion parameters were spectral acceleration at 1.3 TS and magnitude. And of course, afterwards, we validated this method. It's a 2-part method, like the Bray and Travis Zero method, where we first look at what's the probability of negligible displacement, because it doesn't matter if you have 1,000th of a centimeter or you have 1/10 of a centimeter. They're very different numbers, but in terms of an engineering performance level, they're the same value. They're basically negligible or 0. And so the probability of 0 displacement goes up rapidly as the yield coefficient, dynamic resistance, increases. And the chance of getting 0 displacement goes down rapidly as you get to large ground motions. Then you have to look at the non-zero displacements, and we use 0.5 centimeters as the threshold. And of course, that's going to depend on the yield coefficient and decrease as that increases. It will increase as spectral acceleration increases, and then we need to bring in magnitude because it represents duration. Those 2 parts can be looked at individually, and you can look at things about sensitivity to the fundamental period, sensitivity to the yield coefficient. In fact, one of the valuable things about this analysis, you can very quickly look at what matters before you get into detailed analysis. And then those can be combined to get you the more familiar logarithmic of seismic slope displacement versus yield coefficient. And let's just focus on one TS value and one acceleration level. Besides estimating that value given a yield coefficient, you properly get the uncertainty and the range of displacements that are possible from 16th to 84th percentile. And there's a spreadsheet at my website that you can use that does this correctly. In performance-based design, which is the focus of this conference, this is one of the more important things. If you decide for a project that 30 centimeters is the threshold for satisfactory performance, then you can do the sensitivity analysis and realize I don't need to invest any more money if KY is 0.2 to 0.3, because it doesn't matter. The chance of getting more than 30 centimeters is low. On the other hand, if KY is very low, it doesn't matter what the TS is within a reasonable range. I've got a large chance of getting a displacement greater than 30 centimeters. In this middle range, for this particular problem, there's significant sensitivity to TS. And so it's saying, okay, this method needs to be thought of in that way, and also more advanced analysis is probably warranted. The thing that Dr. Travisero and I looked for back in the early 2000s that we didn't see was the effect of forward directivity pulse motions. We thought it should be there, we just didn't have enough ground motions. Well, now we have an order of magnitude more near fault pulse motions. And you can imagine that having this kind of velocity pulse and this kind of directivity should affect the seismic slope displacement. A slope that's oriented in that direction should move more than a slope that's oriented in the orthogonal fault parallel direction. And so we took all the pulse motions and we went through and rotated to calculate the acceleration time history at 1 degree, 2 degrees, 3 degrees, at 180 degrees, and then pushed them all through our model to calculate displacement, and then found the orientation that calculated the maximum displacement for those two horizontal components. That orientation gives us the D100, much like what we do in ground motions. And obviously the median is the D50. There's a significant difference between the D100 and the D50 for near fault pulse motions. We have to bring in PGV, which is not surprising because it defines the intensity of the pulse motion. And the bottom line is, if you have a system that's oriented to where it's going to move within 45 degrees of the fault normal direction, and you anticipate forward directivity, you should use the D100 component as your estimate. And if you're in an orthogonal to that, you can use the D50. This method has been validated against 13 well-documented case histories. I just pulled out a couple, 6 cases here. Some landfills that were shaken by the Loma Prieta earthquake that had very little observed damage or movement, and the method is consistent with that, and essentially say you should not have an issue. A couple of dams that were very strongly shaken that had displacements on this order. I deliberately included this one because you should occasionally get a value outside of the 16th to 84th percentile range. But it provides an index that there's going to be some movement, and there's very little chance of getting zero displacement. And then we have the cases in Northridge for pulse motions for landfills, where the 16th to 84th percentile range captures what was observed. That method is for shallow crustal earthquakes along active plate margins. We should also look at subduction zone earthquakes. In fact, in 2018, working with Jorge and Dr. Travisero, we developed this model because I saw people using our model in South America for subduction zone events. So we focused on interface and developed that model. Well, NGA here has developed ground motions in subduction zones. So Jorge Macedo has taken advantage of that. And so where we had 800 equivalent ground motions, now there's 6,000 interface motions available. And very importantly, we did not look at IntraSlab, and the IntraSlab motion database is available. And I'm pointing this out here. The dashed lines are the interface model that I developed in 2018, which is very consistent with the new model. That actually hasn't changed much. 800 to 6,000, 800 is enough motions to where I think we're pretty stable. The big difference between these models is the difference between the within slab and the interface model. And so do not use a interface model or a shallow crustal earthquake model for an intraslab event. Use the intraslab model by Macedo et al. So ending up talking about performance-based design, normally we have been doing this deterministic analysis where, based on the governing magnitude and distance, we estimate the spectral acceleration at the 50th percentile or the 84th percentile, and we calculate our displacement. More recently, people have been using probabilistic seismic hazard assessment to get the spectral acceleration, and then use that spectral acceleration at the selected return period, 475-year return period, to calculate the seismic displacement. Why stop there? Why not use that information with the displacement model to estimate the displacement and develop a seismic slope displacement hazard curve? The seismic slope displacement hazard curve is taking the information from the spectral acceleration hazard curve and taking off enough points to get the shape of that, and then do calculations with a uncertainty and variability of ky, the TS, as well as getting the SA and the magnitude from this curve. And it's pretty straightforward with this straightforward model to develop directly the mean seismic slopes displacement hazard curve, where you can look just directly on the hazard which matters to you, seismic slope displacement. One of the wonderful things about this is by looking at you have the ground motions typically in the hazard curve, but you can include other things like the magnitude and the rate effects. It can, very importantly, the uncertainty in strength, which leads to the uncertainty in the yield coefficient, the uncertainty in shear wave velocity, which leads to the uncertainty in TS. You can include all of those and end up with fractals and multiple hazard curves that can be run relatively efficient in today's world, and come up with the mean curve. But you can also look at the uncertainty associated with your estimate and think about the scientific uncertainty as well as the aleatory uncertainty from the ground motion, and pull all that together to inform your decisions. Let's look at one example. This is in San Francisco, at Yerba Buena Island, a fictitious large fill there that has a initial fundamental period of 0.67 seconds. Initially, we're saying foolishly that there is no uncertainty in KY and TS. Then we have some marginal amount of uncertainty with the coefficient of variation of 0.2 and 0.1 for KY and TS respectively. And then we increase it to a number that maybe is more appropriate where we really don't have good information, 0.5 and 0.25. Let's take just the curve at KY equal to 0.04 and the curves for KY equal 0.3 to look at the impact of this. When it comes to the 2475-year return period, don't worry as much about the uncertainty estimate of the uncertainty, or your uncertainty in estimating uncertainty, because the difference is not that large in terms of 200, 250. They're basically giving you the same information in terms of we're going to get a couple of meters or so of movement. At different KY values, this always depends. You get a ratio of almost more than double. So it tells you about that uncertainty. For this case, we deliberately picked two locations in the western part of the United States that happen to have the same spectral acceleration at 475 years. Because of the shape of this hazard curve, they're going to have different seismic slope displacements. So we should not be looking in terms of spectral acceleration hazard. We should directly be looking at seismic slope displacement hazard curves. Another important thing is selecting ground motions. This is a case in Seattle where if you look at spectral acceleration and look at the 2475-year return period, and you look at deaggregating the hazard by the seismic source, it would suggest the most dominant source is shallow crustal earthquakes. And that might bias you towards selecting more ground motions to represent that source. But if you look at seismic slope displacement, which is what you really care about for this project, then it's dominated by the interface event, because the duration effects are much more significant for seismic slope stability than they are for the other intensity parameter. And so moving to a site that's away from the coast in Peru, where the intra-slab, the within slab event is actually governing, just like you develop deaggregation and understand the contribution of distance and magnitude or spectral acceleration or peak ground velocity at or some intensity measure, that can be done with the hazard curve if you do it in terms of seismic slope displacement. And so you can select ground motions that represent the magnitude and distance that governs the hazard at whatever return period you're looking at. So performance-based design really is here because we can do these convolutions and we can do these models very quickly. So in conclusion, never forget the most important thing is to focus on severe strength loss, because something like flow liquefaction or very sensitive clays can lead to large deformations, and you don't need to try to estimate those amounts. They're going to be large, and you need to mitigate them or address that potential flow hazard. When you don't have that, then you do need to be able to evaluate performance, and the way you typically evaluate performance is in terms of a calculated seismic slope displacement. I'm offering the Bray and Macedo 2019 update to Bray and Travazzero 2007 for shallow crustal earthquakes. It captures the dynamic resistance of the slope with the yield coefficient. It brings in the fact that the earthquake shaking for a non-rigid system is better reflected by the spectral acceleration at 1.3 times the initial site period, because there is some degradation, as well as magnitude to represent duration. And if you're close in and you have high peak ground velocities, you have to also bring that in. So we have a separate model for near fault ground motions, which bring in PGV. The dynamic response of the sliding mass is brought in, and you get the coupled displacement. The Macedo et al. 2022 model brings in interface and, very importantly, intraslab subduction earthquakes. And so it's a robust way of looking at that. The seismic environment matters. And then last but not least, hopefully you see some of the opportunities you have with using these simplified methods as an index of performance, but putting them in a probabilistic sense, because the most important issue is the ground motion and how it affects the slope and how much it moves. And so by using a seismic slope displacement hazard curve, you can understand the uncertainty of the ground shaking and couple that with the uncertainty of the slope properties to better make informed decisions in terms of what's the performance of the system in a performance-based assessment. Thank you.
I think everybody has gone quiet. So I'll say thank you for that excellent lecture, John. As always, very clear and concise. And thank you for keeping to that time as well, so accurately. Shida, you want to take on and invite some questions, or are we going to do that at the end?
We can do that at the end. Just looking at the timing of the presentations, I think we need to go take one, and then we can have, if that's okay with you, questions at the end.